Hello and welcome to G Fun Facts Online, your go-to spot for uncovering the amazing science behind our world. I am your host, and today we're diving deep into a topic that affects all of us, plastic. Specifically, one of the most common plastics out there, polyethylene, or PE. Think plastic bags, bottles, food containers. Yeah, that stuff. It's everywhere. And unfortunately, that means a lot of it ends up as waste, creating a huge environmental headache. But what if we could turn this plastic problem into a plastic solution? What if we could take old, discarded polyethylene and transform it into something new, something valuable? That's where the exciting field of chemical upcycling comes in. Forget traditional recycling that often just downcycles PE into lower quality stuff. We're talking about breaking it down and building it back up into better materials, helping create a true circular economy for plastics. Sounds like science fiction? Well, it's happening right now, and the advancements are pretty mind-blowing. So let's explore some of the ingenious ways scientists are trying to give polyethylene a new lease on life. First up, let's talk about heat and catalysts. One of the main techniques is pyrolysis. Imagine taking PE and heating it up really hot, but without any oxygen around. This breaks it down into a mix of useful stuff like gases, oils similar to diesel fuel, and waxes. This pyrolysis oil can be used as fuel or even further processed into brand new chemicals and plastics. Now, it's not without its challenges. You have to carefully manage any harmful gases, and it can be complex and costly. But scientists are smart. They've found that adding catalysts, think of them as chemical matchmakers, can make pyrolysis more efficient. This is called catalytic pyrolysis. For example, researchers have used special catalysts like zeolite-based ones, or even cool new graphene-based metal organic frameworks, or GMOFs for short, to selectively produce specific chemicals like propylene, which is a key ingredient for making polypropylene plastic. So old PE could help make new, different types of plastic. Then there's hydrocracking, also known as hydrogenolysis. This method uses hydrogen gas along with a catalyst to chop PE down into shorter chain alkanes. These are valuable as lubricants, waxes, or fuels. Ruthenium-based catalysts are super active here, but ruthenium is pricey, and it can sometimes produce methane, which isn't ideal. So, researchers are also looking at more budget-friendly options, like nickel-based catalysts, which are showing great promise. Some catalysts, like cobalt on CSM5 zeolite, are even champs at turning PE specifically into propane. And let's not forget gasification. This process uses high temperatures and a controlled amount of oxygen or steam to convert plastic waste into something called syngas. Syngas is a super versatile mixture of hydrogen and carbon monoxide, and it's like a basic building block that can be used to make all sorts of different chemicals and fuels. Okay, moving on from just heat, how about some clever chemical teamwork? This brings us to tandem catalysis and co-reactant strategies. One really innovative idea is to react PE with carbon dioxide. Yes, the greenhouse gas CO2. Using special catalysts, scientists can convert PE and CO2 into aromatics like benzene and toluene, which are important industrial chemicals, and also carbon monoxide. What's extra cool is that this process can actually use up excess hydrogen that might otherwise be wasted to turn that CO2 into useful carbon monoxide. Talk about a win-win. Another strategy involves catalytic depolymerization with co-reactants. Here, other simple molecules like light N-alkanes or ethylene are added into the mix. These co-reactants help steer the chemical reactions, allowing PE to be converted into specific products like liquid fuels or lubricants, often at lower temperatures. And check this out. Researchers at UC Berkeley have developed a process using a combo of relatively cheap solid catalysts, tungsten oxide on silica, and sodium on gamma alumina. This dynamic duo can efficiently convert PE and even polypropylene or mixtures of plastics into propylene and isobutylene with really high yields, over 90%, at around 320 degrees Celsius. And it doesn't need a pre-treatment step called dehydrogenation, which is a big plus. Plus, these catalysts are reusable and good for continuous processes. Smart stuff! Now let's shine a light on some other approaches: photocatalysis and electrocatalysis. Imagine using sunlight to fight plastic waste, That's the idea behind light-driven photocatalysis. Scientists have developed methods that use sunlight and non-toxic photocatalysts, like titanium dioxide paired with tiny amounts of metal catalysts, like palladium. This setup can convert PE waste into valuable chemicals like ethylene and propionic acid, all at room temperature. It's a greener, less energy-guzzling way to go from waste to value. There's also photoelectrocatalysis, which combines the power of light with electrical energy to help break down and transform plastics. What about something a bit different? How about molten salt catalysis? This is a really neat approach that uses a mixture of Lewis acidic aluminum chloride and sodium chloride, basically a hot, salty liquid bath, as both the catalyst and the reaction medium. This process can upcycle PE into liquid alkanes at relatively low temperatures, below 200 degrees Celsius. And the best part? It doesn't need any external solvents, hydrogen gas, or expensive noble metal catalysts. It works through a clever repeated cracking and alkylation pathway. And the innovation doesn't stop there. We also have some emerging and combined approaches. Hydrothermal treatment, or HTT, is a newer kid on the block. It uses supercritical water. That's water heated under pressure until it acts like a special solvent to dissolve and break down mixed plastic waste. Because it doesn't involve direct burning, it could produce more useful products and fewer toxic nasties than traditional pyrolysis. It still needs some tweaking for large-scale use, but it's promising. Then there's hybrid chemical/biological upcycling. This is like a two-pronged attack. First, plastics get a chemical pre-treatment to make them easier for microbes to munch on. Then, these amazing microorganisms can degrade the plastic further or even convert it into valuable bio-based products. This is more developed for plastics like PET, the stuff in water bottles, but research is actively looking at how to apply it to PE. And finally, there's macromolecular transformation. Instead of completely breaking PE down into tiny molecules, this approach focuses on modifying the existing long polymer chains to create new materials with different, useful properties. It's like giving the plastic a molecular makeover. So, with all these incredible methods, what are the big goals? Why are scientists working so hard on this? Well, firstly, and most obviously, to reduce the mountains of plastic waste, choking our landfills, and polluting our environment. Secondly, to create valuable products from this waste, making plastic recycling economically attractive and fostering a more circular economy. Thirdly, to decrease our reliance on fossil fuels for making brand new plastics and chemicals. If we can reuse what we've already made, we need to drill less oil. And fourthly, to lower the energy consumption and overall environmental impact of dealing with plastic waste. Now, as exciting as all this sounds, there are still some major hurdles to overcome. Scientists need to get better at controlling these reactions to get high yields of the specific products they want. Real-world plastic waste is often a messy mix of different plastics and contaminants, which can mess with the chemical processes. Developing catalysts that are cheap, durable, and effective is another big one. And, of course, scaling up these laboratory breakthroughs to an industrial level that can handle the sheer volume of plastic waste is a massive engineering challenge. Plus, we always need to make sure these new methods are truly energy efficient and environmentally sustainable in the long run. But despite these challenges, the progress in chemically upcycling polyethylene is incredibly promising. Continued research, innovation, and collaboration are key to unlocking the full potential of these technologies. Imagine a future where plastic waste is no longer a problem, but a valuable resource. That's the future scientists are working to build. And that's our deep dive into the world of polyethylene upcycling for today on G Fun Facts Online. I hope you found it as fascinating as I did. Join us next time for more amazing science stories. Stay curious, everyone.